Oh, really? Okay. All right. Anybody? Anybody? I heard the word water a lot. Water. All right. So it's when good. Aqueous reactions. This seems so quiet today. Aqueous reactions and solution stoichiometry. So aqueous means water, right? I heard someone say the D word, dissolved. Yeah, you're like, no, dissolve. So listen, and in last chapter, I used plenty of examples that were just like this. So you're like, this is exactly the same, but it's slightly different. It is a reaction that happens in an aqueous solution, which means, just for a second, we'll get there on the next slide, but so instead of NaCl plus whatever, it's really Na plus Cl minus plus whatever. We're taking salt water or salt, we're putting it in water, it breaks apart and its ions are reacting, not really the whole thing. That's really the only difference. It's not that awful, except for now we have to account for each individual atom instead of just the compounds. So it just adds a little bit more. But some good news is a lot of the answers are the same values, and those are reasonable, and hopefully we'll get through it. Okay, and then solution stoichiometry, then that just means math. It means math. So don't write this down, but you'd have something like AgNO3, and then it'd have an AQ. Plus, we'll just say NaCl, and then an AQ, and then an arrow. What this means is an aqueous solution of this is added to an aqueous solution of this. It means these things are broken up. It means I have Ag plus NO3 minus plus Na plus Cl minus, and then my arrow. When these things react, that part's not hard. You think, all right, Ag must go with Cl. We've done that before, right? And if not, we'll practice it still. And then we have Na and NO3. One step that we'll have to learn is why this one's a solid and this one's an AQ. And that has to do with what we call the solubility rules. So then we'd say, all right, this goes to AgCl solid plus Na plus NO3 minus. Now, it's not horrible at all. You have to know why this one sticks together, why that one doesn't. And then we'd have to do some math. Like that's the stoichiometry part. You'd have to say, hey, we had X of this, Y and Y. How much of this stuff are we going to make? It's the same math, just a tiny bit more difficult. And this is like real life chemistry. All right, now you don't have to get crazy here, but most of you probably went to at least 10 minutes of activities on the football field in the dark on homecoming week. Okay, a lot of you broke eye contact with me at that moment. All right, I'm not judging. If I was in high school, I would have been there as much as I could. Like, I kiss people out of your league, sign me up. I would have been there. But how, like, some people don't ever kiss anyone at True B, right? They just watch. That sounds creepy, but whatever. Well, they do. Am I wrong? I'm not. So look right here. Some people at True B were there, but really didn't do anything. In this reaction, Na and NO3 were alone on the left, and on the right, where are Na and NO3? Still alone. So who true bead? Ag and Cl. Well, everyone else just laughed in the circle. It's sad, bad, but it's real. Okay, this is real chemistry, my friends. Okay, so we're going to learn all about this stuff, and it's kind of cool. I want you to think about how much of this was there and how much of this is there compared to how much is left and left. Worst sentence in my life, but I think someone knows what I'm trying to say. How much were they before? Who cares? It's the same as how they were after. So is there much math with these? No. Yeah, it's the same number. Now, these combined, right? So both of these go down, and the amount of this produced depends on the limiting reactant. It doesn't go away. Limiting reactants never go away in AP Chem. Okay? So it's actually really similar, just with the twist that makes it take a teeny bit more paper. Okay, we ready? That's your future. My expectations is that you can be given two solutions, predict what makes a solid, what is a spectator, and then do all the math. Okay, they are literally called spectator ions, so you're all laughing at me. Okay, so here's some background information. Oh, it works perfect. It is a good analogy. There's a reason why they call chemistry chemistry. You're welcome. All right, solutions. We haven't talked about solutions yet, right? Make sure you never forget what a solution is, because we're going to have, this is probably a 3-week-long unit, and we're talking about solutions. So if you don't know that word, it's going to be a struggle. All right, a solution is a homogeneous mixture of two or more pure substance. The solvent is always present in the greater amount. For us, the solvent will be the liquid, and then the solute is another word, will be the solid. So if I were you, I would draw this beautiful picture right here. This E looks a little weird, though. It looks like a P. All right, so this beaker has a solution of salt water. In that solution, we have what we call a solute, which is the solid, dissolved in the solvent, which is the liquid. It doesn't have to be that way, but it will be that way this entire lab book or unit. This is actually only the second unit of the year. The first 3 chapters are unit 1. Chapter 4 is unit 2. When we used to teach this class in just 2 trimesters, chapters 1, 2, and 3 were on your own. Oh. I know. Yeah, it's okay. Our pass rate was pretty low. I wonder why. It's because no one knew what they were doing. Oh. But back then, regular chemistry was a prerequisite to this class. Oh, really? So that helped. All right, so that's what a solution is. I'm moving on. All right, there is a word, it's called dissociation. I will mispronounce it a lot. I will call it disassociation. Doesn't matter, I mean the same thing. You okay with that? Dissociation is when an ionic substance dissolves in water. The solvent pulls the individual ions from the crystals and solvates them. Okay, dissociation is not just dissolving. They are slightly different, even though they are used like the same all the time. And I'll tell you why. Hopefully I already have it written. I have it right below. Okay, so we should know, based on our ability to consume drinks that are sweet, we know sugar dissolves, right? So sugar is a soluble substance, but sugar does not dissociate. And here's what I mean by that. So sugar is a large chunk. I put it into water and we say it dissolves to form smaller pieces. That is a true statement. Sugar dissolves. But salt dissociates, and I should probably put and dissolves.
Wait, so dissociation is when an ionic compound does it?
Yep, what a molecular one does. Yep. Okay, so salt, when we put it in water, it dissolves into small pieces, but it also dissociates or is solvated, which is another weird term, but that's okay. So what that means is that the actual Na plus and Cl minus are pulled apart from each other. They disassociate. All right, this only happens with ionic or acidic substances. So sugar, when you put it in water, the C6H12O6 doesn't break apart into carbon, hydrogen, and oxygen. It stays a molecule. It just becomes a smaller one that we can't see anymore. You're right, Abby? Okay. What was this? Okay. Yeah, I've always thought you were cool. Okay, so here's an example. This is an ionic substance. This is an acidic substance. Tell your lab partner what H2SO4 is called. Oh, man. Oh, who said that? There we go. It is called sulfuric acid. So many of you said hydrogen sulfate, which it's made out of hydrogen and sulfates, but it is sulfuric acid. Okay, when it dissociates, it breaks into three parts: 2 hydrogen or H plus and 1 SO4 minus 2. So it dissolves and dissociates. Okay, it's a little bit tricky. Yeah, when things, if I write out a dissociation reaction, it has to be balanced. So the subscript just becomes the coefficient. Now you might think, wait, should it be an S plus 4 O's? No, because we've learned that SO4 is its own little polyatomic ion with a charge of -2. We can heat it. If we heat it hot enough, the S and the O's will break apart. But yeah, just putting them into water, no, they do not dissociate. I have this picture. Okay, so you don't have to draw this out, but just to explain what dissociation is. Pretend this is my NaCl. Na is a positive charge in the ionic compound, Cl is a minus charge in the ionic compound, right? So what happens is you put it into water, and the plus sign on the Na, the positive charge, is attracted to all the partial negatives that are on water, which is a polar substance, which you learned in biology, right? Yeah. All right. And then the minus is attracted to all the H pluses that are slightly, I shouldn't say H pluses because they're not really, the slightly positive hydrogen ends of the water molecule. If you get enough H's to attract to the negative Cl and enough positives, I said this backwards. If I said it backwards. If you get enough H's to attract to the negative Cl, all right, and then enough negatives of the oxygen to attract to the positive Na, then they will pull each other apart. And when this is broken, we say it is dissociated. They are now in a solution that is an ionic solution. Ooh, there's a lot of talking. All right, so an electrolyte. This is another vocab word that you should know. Yeah, you hopefully should. I don't know. It should be exactly the same, but I don't know how he teaches. So substances that dissociate into ions when dissolved in water are considered electrolytes. Where do you think they get that name? Electrons. Good. That's a good guess, and it is definitely related. An electrolyte is something that will help water conduct electricity. Did I demonstrate electrolytes for you this year already? I haven't. I swear I did. I didn't pull out like the death trap. It's okay. It's not for you. It's for me. I swear I did it already this year, though. I'm so confused. So if you have not seen this thing, okay, I'm going to plug it in and then you lick it. I'm just kidding. Okay, so I will get some stuff. An electrolyte is a solute that, when placed in water, causes the solution to conduct electricity. Tell your partners how excited you are for this chapter while I go get some stuff. Yeah, it'd be bad. Okay, so this is a light bulb, and it will turn on if I touch the wires. It would kill me too, but it'd turn on. All right. Or if I put it in something that conducts electricity, it will light up. Easy enough. So it's a good electrolyte tester. So on this little table I have, it's a cart. I realize that now. Thank you. Okay, I'll just put water in this one. Notice my birthday is less than a month away. Thank you. What's sad is when school is not on my birthday. It is my greatest day of collecting Mountain Dew of the year. This is HCl, hydrochloric acid. No, that's water from the tap. Yep, go. All right, I have water from the tap, hydrochloric acid, distilled water, and a clean beaker. This failed last year. We'll see if it works this time. It was pretty funny. Don't worry about it. Distilled water, and then I'll put vinegar. I hope that's isopropyl alcohol. Yeah, might as well. Yeah, I was actually the bartender in The Greatest Showman. Oh no. Yeah. Hold on, I need vinegar. You guys are in charge. Remember the order I put them in. All right. And then I brought some salt. Sound good? Good answer. Okay, then I have vinegar. Okay, are we ready? We paid a lot of attention. We know where everything goes, right? All right, so this will light up if I put it in things that conduct electricity. So tap water, right? I won't. Tap water. Oh, fancy. Okay, lights off. Everything's better in the dark. All right, so that was tap water. What was next? Hydrochloric acid. Ooh. So hold on. Which one of those two do you think is a stronger electrolyte? Okay, then I had distilled water, right? Okay, we'll put that in there. Oh, absolutely no non-electrolyte. Pure water does not conduct electricity. So before you ask, can you take a bath in distilled water and drop the blow dryer in? No. Okay. The moment you get in your bath, you add electrolytes and you would die. Isopropyl alcohol, nice and cold for some reason. Why would we think that isopropyl alcohol is not an electrolyte based on our definition so far? It does not ionize. Very good. It doesn't dissociate. What was this one? Oh, the vinegar. All right, here we go. So vinegar is an acid, right? Acetic acid. This is hydrochloric acid. So if you compare the two, well, you tell your partner, how do the two compare?
Wait, can you put them together? Nothing.
Weird, it doesn't go through the air between the glasses? That's bull crap. I can mix the liquids. I don't want to, but I can. Do you want me to?
Yes.
Okay, hold on. Tell your partner first how you would define vinegar compared to hydrochloric acid. All right, so the request has been made to mix them together. I don't even know the order anymore. It's a disaster. Ooh. So how could I tell which one of these is hydrochloric acid based on this? The brightest one. So it's either this one or that one. All right, so hydrochloric acid, distilled. I wanted distilled. That's how I started before, right? Then then I had the alcohol.
Probably also tell by drinking each of them.
Well, what's that?
You can also probably tell what they are by drinking.
I could. So there's our mix. Alcohol. Okay, now this doesn't work as good as you would hope. Ow.
You got this, David.
All right, but we have a non-conductor, right? Whoops, right here. Okay. I don't trust myself. Okay. So I'll just add some salt. All right, then I'll stir it up for a second with my scissors. Okay, now this was distilled water. It didn't conduct at all, right? That was distilled water. So we would say that NaCl is a what? It's a really good electrolyte.
So like we put some salt into the tap water with that.
Yeah. It won't because it's a crystal. There's no Na plus or Cl. In order for it to be electrolyte, we have to have imbalance in charge. We have to have pluses and minuses. But just a pile of salt, we can try it. Tim, you're in charge of putting this back in. Weird. All right. Now there is a question. I don't want to do this, but you tell me, tell your partner, not me. What would happen if I put the salt in the isopropyl alcohol?
I don't need to be support by that one.
All right. Any theories? All right. So everyone listen to Tim. What'd you say, Tim? Timmy, what'd you say? Good. It won't do anything. It'll go to the bottom and it would just stay there because salt dissociates in water, but it won't dissolve in isopropyl alcohol. Okay. Yep. If it doesn't dissolve in the first place, it won't dissociate. But it's all over. I unplugged that, right?
Yes.
Okay. All right. It is actually very dangerous. So I'm not overreacting. It's bad. Okay. A non-electrolyte may dissolve in water, but it does not dissociate into ions when it does so. So tell your partner the name of one of those. Sugar. Dirt's tricky because dirt doesn't really dissolve. If it dissolved, the water would mostly stay clear. So it kind of mixes up, makes what we call a colloid. But anyway, all right. So sugar, we all right with that? Okay. Soluble ionic compounds tend to be electrolytes. Now, a lot of ionic things are electrolytes. Hold on, I'll go there in a second, but not all of them. It's October, so there's your foreshadow scary moment.
Wait, so is nitrate not electrolyte?
No, it's the best electrolyte we have. I know what you're thinking. In that reaction, it didn't do anything on either side. Is that what you're thinking? Okay, that actually means it's really good at being an electrolyte. In order to be electrolyte, they have to be separated. Nitrate doesn't stay together with anything. But silver and chlorine are not usually very good electrolytes. We'll learn. Okay, now notice once again, a lot, most, almost all ionic things are soluble, which means they are electrolytes, but definitely not all of them. So let's go back here in a second. We talked about this before, right? This substance, silver nitrate, very soluble. Silver nitrate is a very good electrolyte. I'm just going to put that. NaCl, we just saw evidence, right? That's a good electrolyte. Sodium nitrate, one of the most soluble dissociatable substances there is. But this stays together as a solid, which means AgCl is a non-electrolyte. So what this means, kind of stick with the picture I drew before. Remember, water was able to pull these apart. If something's soluble, then the attraction of the ions to the water is stronger than the attractions to themselves. Now let's talk about AgCl, that in a solution stays solid. That's supposed to be an S. We'll learn those. If something is a non-electrolyte, the attractions between Ag and Cl are stronger than the attractions between Ag and the oxygen in water and Cl to the hydrogen in water. Water is a great thing at pulling things apart. But if the things are stronger, then water can't pull them apart. They stay together. And we say they're not soluble or they are non-electrolytes. Who's sort of with me right now? Okay. All right. What if you marry who?
You married your brother.
Mother? Even weirder.
It don't matter. It was weird either way.
They're all weird. Move on. Okay. So molecular compounds tend to be non-electrolytes except for acids and bases. Most bases are ionic compounds. The acids are usually not defined as ionic compounds, even though really they are. Okay, but sugar, isopropyl alcohol, gasoline, grease, fats, oils, all those things, they are considered non-electrolytes. If I put that in vegetable oil, there'd be no conducting. That simply means they stay together. Their intermolecular forces, is the fancy name for them, are stronger than water's ability to pull them apart. All right, and we already said this, but a strong electrolyte dissociates completely when dissolved in water. So we're going to use the following terms. We're going to define something as a strong electrolyte, a weak electrolyte, or a non-electrolyte. So of my examples, tell your partner right now, maybe label them on your paper too. What would you guess were strong electrolytes, weak electrolyte, and non-electrolyte? Of my examples. All right, so what would isopropyl alcohol be? Non. The alcohol didn't conduct at all. So that's a non-electrolyte. I would not, but I could put my finger in there and those things in there and nothing should happen. Now I'm not going to. Who knows how clean my finger is and if that would just kill me dead. All right, what would vinegar be? Vinegar's a weak. It is weak. The light didn't go very bright, right? And then hydrochloric acid, strong. And then water, non-electrolyte. Tap water, weak electrolyte, but they're not going to ever ask that on a test. Just know water is a non-electrolyte. But salt water was definitely strong, right? Yep, it's always assumed it's pure water. Say that again. I'd love to. Okay, I really want to draw a picture real fast, and I want you to put it in your notes. Yes, I do. Okay, do you see the symbolism here? A strong electrolyte in a solution of the things that are present, the amount of H plus and Cl minus are huge compared to the amount of HCl present. So a strong electrolyte, the ions dominate in solution. So weak, vinegar is HC2H3O2, and then you'd have this picture can help a few of you. It's showing the relative concentration for a weak electrolyte. Most of it is contained as the molecule, and only a little bit of it is the ion. Versus strong, where it's there. Now, I know I'm going fast right there, but a non. Nothing. Doesn't dissociate. Now, the real truth is it does, but it's 0.00000001 molar, which we're just going to assume is 0. Okay, if you, I don't know that I'll have them online tonight, but you may see your grade on the internet tonight. Yes.